So this set of past paper questions goes alongside the notes you're looking at for atomic structure. The questions are set into 3 sections. First one's on relative mass, so looking at calculating relative atomic mass, working out protons, neutrons, electrons, things like that. Second section is on mass spectrometry, and the third section is on electronic configuration. So it's worth looking at these questions alongside the notes just to check you're actually understanding what's going on in the notes. Again, just to remind you that the mark scheme is at the back of this PDF, so you can check your answers very quickly as you go along. Though in this video I'm going to work through a bit more slowly all the questions, so that if you're stuck on one or the mark scheme doesn't make sense, you can check this video and hopefully it'll be a bit more clear to you. So the first question, we're told about hydrogen. It says there's 3 naturally occurring isotopes: protium, deuterium and tritium. That was kind of briefly mentioned in the booklet you have. Part A, draw an atom of tritium showing and labelling all the subatomic particles present. That's not too far different to questions you did GCSE. You had to draw atoms. Obviously, this wee bit tricky here is asking about tritium. So we think about what tritium is. It's given kind of that symbol with a 3 up top. It is still hydrogen, therefore its atomic number will still be 1, because the atomic number defines what the element is. The number up top must be the mass number, because that's the one that's changing between isotopes. And if you remember your definition of isotopes, they're atoms of the same element with a different mass number. So that must be the mass number. Think about protons, neutrons, electrons. That's what we're working out here. Must have 1 proton because that is the atomic number, and it has to be 1 proton for hydrogen. Neutrons must be 2 because subtracting 1 from 3 gives 2. And electrons, still the same as protons, should be 1. So we're looking for something with 1 proton, 2 neutrons, and an electron outside it. Not too complicated, so I might shade a proton in, but it's up to you. Maybe just make them look different from the neutrons. And even though, as we'll look at later, we're going to change this kind of shell structure and update it a wee bit. If you're just drawing an atom, you can just do like a GCSE model. So do a shell, put an electron in there. Importantly, you have to label it to get the marks. So that's an electron, that's a proton, and here are 2 neutrons. Just call them neutrons. Part B. The relative atomic mass of hydrogen is 1.0079. Explain which one of the hydrogen isotopes is the most abundant in nature. So it's quite a tricky question, this. It almost looks like you're about to have to calculate the relative atomic mass, sort of shaping up for that. But they're giving you the answer. They're telling you the relative atomic mass is 1.0079. It's asking you which one from the information of protium, deuterium or tritium, 1, 2 or 3, must be most common. If you think about it, we've got 3 options here. H1, H2, H3, this is a mass of 1, mass of 2, mass of 3. What we're saying is if we take into account how much of each there is, so like the relative abundances of each one, and work out the relative atomic mass using that fraction we normally use as a calculation, the answer comes out as 1.0079. In other words, very, very close to 1. So it's not up at 3 or 2, it's very close to 1. That therefore must mean that the one which has a mass of 1, protium, must be the most common one, because your average takes into account how much of each there is. So if your final answer comes out very close to one of them, it must be the most common isotope. So our answer there is that protium is the most common one. You could just write H1, I think. And the justification for the second mark is that the value for the relative atomic mass is very close to 1. Question 2. All naturally occurring sodium atoms have a relative atomic mass of 23. However, radioactive isotopes of sodium may be prepared. So basically saying you could have 2 different isotopes of sodium. Normally it's just 23, but you could synthesize a 24 one. Part A. State the number of electrons, protons, and neutrons in an atom of 23 sodium. So again, that's just like a GCSE style question. So electrons, protons, and neutrons. What we're looking for here, well, let's look at, we have to use periodic table. So sodium in the periodic table is an atomic number of 11, therefore must have 11 protons. Assuming it's a atom, which is, can't be charged, has to be neutral, therefore must have 11 electrons as well. Neutrons is just the mass number, take the atomic number, 23 minus 11 is just 12. Explain why 23 sodium and 24 sodium are regarded as isotopes. It's basically just asking for your definition of an isotope. So one way of answering that is same atomic number, different mass number, because that's what your definition of isotopes is. Absolutely, there's a different way of answering as well. You could say that the same number of protons, different number of electrons. different number of neutrons. Again, it's kind of much the same thing. So 6 of one, half dozen the other. If you're not sure in the exam, there's nothing wrong with writing both down because they're both correct. So if you think maybe one won't get you both marks, you can stick them both down because they kind of mean the same thing. Question 3. There are 5 isotopes of germanium. Atoms of the germanium-74 isotope contain 32 protons, 32 electrons, 42 neutrons. Complete the table about protons, electrons, neutrons. That question could be straight off a GCSE paper. It's exactly the same. So protons have a relative mass of 1, electrons 1 over 1840. That's just out the notes. Neutrons 1. Relative charge, protons plus 1, electrons minus 1, and neutrons 0. Pretty generous 3 marks for that one. State in protons and neutrons the meaning of the following terms: mass number, atomic number, isotopes. So the first 2 parts are fairly straightforward. So the mass number is just the number of protons plus number of neutrons. The atomic number is just number of protons. You have to be careful of isotopes because I'm just after saying that you can define isotopes as having same atomic number, different mass number. They put a twist in this question here in question 3. You have to state your answer in terms of protons and neutrons. So you couldn't use mass number, atomic number. You have to explain it in terms of same number of protons, different number of neutrons. So atoms, which have the same number of protons, but different number of neutrons. Part C. The term atomic number, mass number can be used to deduce the number of protons, neutrons, electrons in an atom or ion. The atom has 15 protons and 20 neutrons fewer than there are in a germanium-70 isotope, deduce the symbol and mass number of this atom. So essentially this is a little bit of periodic table work and a little bit of calculation work. So germanium, it's telling you it's germanium-70. That's the mass number of germanium. To work out this question, you also need to know the atomic number. That's not given to you. You have to use the periodic table. If you look up germanium in your periodic table, it's got an atomic number 32. This mystery atom has 15 protons and 20 neutrons fewer than there are in germanium. It's just a symbol and mass number of this atom. So you have to basically tweak these numbers to adjust for what's telling you is different. So 15 fewer protons would make an atomic number of 17. So this mystery element must have an atomic number 17. If I'm removing 15 protons and 20 neutrons, that's going to take away 35 from the mass number, because remember mass number is protons plus neutrons. So taking away 35 from that will give me an answer 35, basically halving it. And if I look at my periodic table, I'm looking for something which has an atomic number 17 and the mass number 35. Well, 17 as the atomic number means it must be chlorine, because that's what makes chlorine chlorine. Its mass number is one of the isotopes, it's 35. Part D, the mass spectrum of germanium used to calculate its relative atomic mass. To determine or define the term relative atomic mass, just a definition out of your notes. It's quite a long one, just make sure you get word perfect. The average mass of an atom, of an element, relative to, you have to remember to mention this bit, 1/12 of the mass of an atom of carbon-12. It's just out of notes, but it does reward your learning there. Question 4. A sample of sodium from a nuclear reactor contains 2% of sodium-24 and 98% of sodium-23. Calculate relative atomic mass. So a calculation we're quite used to from our GCSE days. So I'm going to make my little fraction here. So I'm going to do 24, the mass of the first one, times by 2%, which is the percent abundance of it, plus 23 times 98%, divided by the total abundance altogether. So that's 2 plus 98, which is 100, which is normal for percentages. That's going to put that on my calculator, and that will come out as a relative atomic mass of 23.02, because I have to be careful to do decimal places here. Little common sense check. Remember, your answer should come out as very close to, between the two isotopes you've got. It should be between 24 and 23. 23.02, it's quite close to 23 because that's the most abundant one. That makes sense as an answer. It's not an unreasonable answer. Got a very similar question here for germanium. 5 isotopes this time. You have to work out the relative atomic mass. So it's not much harder, but just a lot more calculator work for this one. So just take your time with the calculator. So 70 times 20.55 plus 72 times 27.37 plus 73 times 7.67 plus 74 times 36.74 plus 76 times 7.67. I have to divide it by the total abundance. Now I have to be really careful here. They can try and trick you out here. Sometimes the abundance doesn't actually add up to 100 if not percentages. So they could do a sneaky one where this actually adds up to 90, for example, and you divide by 90 instead. However, this is percentages, so it should add up to 100. And if I check these numbers, I can just add them up together. I do actually get 100. So I'm going to divide by 100 here. Stick in my calculator, maybe do it twice, just make sure you're not getting the wrong answer. And what you'll end up with is the final answer of 72.7, because they're asked for one decimal place. Common sense check, shouldn't be smaller than the lightest one or bigger than the heaviest one. 72.7 is kind of in the middle, which is kind of where I expect it to be. That looks like a reasonable answer. Question 6, neon has several isotopes, complete the table below. So it's just looking for protons, electrons, neutrons for your different isotopes of neon. Again, that could be a GCSE question. Neon 20, just using your periodic table, because neon has an atomic number of 10. 10 protons for all of them. And therefore 10 electrons for all of them, because they're all just atoms, that doesn't say they're ions. Number of neutrons just changes 10, 11, 12 as you go down the isotopes. Again, it's a very repetitive question. We're asked to work out the relative atomic mass of neon based on those isotopes. So first one has got a mass of 20, going to times it by 92, plus 21 times 0.26, plus 22 times 8.82, divided by 100, because it is percentages, those numbers add up to 100, and that will get me 20.18 to 2 decimal places. Name the isotope used as a standard to compare the relative atomic masses of atoms. Have to be careful here, it's not just carbon, it's one specific isotope of carbon, it's the carbon 12 isotope, is what you use for that comparison.